We define a code word as an n-digit number in decimal notation, so we're using digits from 0 to 9, that contains an even number of zeros, right? So for example, if n is equal to 4, let's say, so 4-digit, if you do 0, 0, 1, 1, this has an even amount of zeros. There are 2 zeros, so this is valid. But if you were to do 1, 2, 3, 0, this is going to be invalid code word. This is not going to be a code word because you only have 1 0, right? Of course, if you have 1, 2, 3, 4, this is valid because you have no zeros, and having 0 is an even number, so 0 zeros would be an even amount, and so on. And so if we denote by an the amount of valid code words of length n, our goal is to find, so we want to find the closed form for this an. And we're going to do this using generating functions. So our first step is we're going to try to find a recurrence. So for this problem, we're going to try to solve it by first finding a recurrence and then using generating functions to solve the recurrence. Okay, so the idea here is that to form an n-digit code word from n minus 1 digits, so let's think about it recursively. So imagine that we first have n minus 1 digits, and then we want to know how we choose our next digit so that now we have an n-digit thing that is valid. Well, there are two cases. So case 1 is that this sequence here, already has even number of zeros. So if it already has an even number of zeros, then we just need to add, we just add a non-zero digit. So for example, if the sequence was 1 0 0 1 and we want to add one extra digit and keep this valid, we only have 9 choices. We can choose any digit except for 0. So we could put an 8 here, but we couldn't put a 0. So how many ways are there to do that? Well, case 1, so how many of these have even number of zeros? Well, that's just an minus 1, because again, an counts the amount of, so an minus 1 counts the amount of n minus 1 code words that are valid, and so they have even number of zeros. And for each one of those, we can add an extra digit. So we have 10 digits, but we can't choose 0, so this times 9. Now, case 2, which will be disjoint from case 2, is what if d1, dn minus 1, has an odd number of zeros, has odd number of zeros. Well, in that case, we must add 0, right? So if you give me a number like 1 0 0 0, so it has 3 zeros, the only option that we can do is to add a 0 to it to make it into a valid code word. Okay, so how many of these exist? So we know that an minus 1 counts the ones that have an even amount. That means that these are the ones that have an odd amount, and they can either be even or odd. So what we can do is we can take all the possibilities. So how many possibilities are there of combinations of n minus 1? So you have 10 choices for the first digit, all the way up to 10 choices for the n minus 1 digit. And then if we subtract the ones that are with an even amount, we get the ones with an odd amount. So this is the ones with an odd amount. And then we must add 0, which means, and that's only one choice, so we multiply this by 1. So this means that an is going to be the sum of these two cases. So 9 an minus 1 plus 10 to the n minus 1 minus an minus 1. And of course, if you just write it out, this is 8 an minus 1 plus 10 to the n minus 1. And so this is a recursion for our problem. And now we can try solving it using generating functions, right? Oh yeah, and of course, we have our initial condition, a0 here. So if you have the one with nothing, then of course you do nothing and you have a 0 amount of 0, so it's even, so a0 is equal to 1. You can also start it at a1 if you prefer, or any number you prefer, but yeah, we'll start it at a0. So this is our sequence, and we would like to then find the generating function for it. So this is going to be a linear recursion, but it's going to be non-homogeneous. We saw how to solve this before. You can solve it also using those techniques with for solving non-homogeneous. We're going to show how to solve it using generating functions, and it's going to go pretty much the same as when we were solving the other recursions with the generating function. So these linear recursions, we're going to be able to write them in, like solve them essentially using the, how do you call it? Using the geometric series. Okay. So let's do this. So let's derive our generating function. So once again, our recursion was an equal to 8 an minus 1 plus 10 to the n minus 1 with a0 equal to 1. And our generating function for this, let's denote it by g of x. So g of x is going to be summation an x to the n and larger or equal than 0. And so the idea here is we'll multiply by x to the n on both sides here and sum over, in this case, over n larger than 1. So let's see this. So let's multiply both sides by x to the n and then take the summation. So it's going to be summation of an x to the n equal to summation of, so 8 summation of an minus 1 x to the n plus, here it'll be summation 10 to the n minus 1 x to the n. X to the n. And where do we start? Well, this equation here is valid for n. So let me write this here. So this here is valid for n larger or equal than 1, right? Because we have that n minus 1 there. So we are going to start at n larger or equal than 1. Okay, and now we want to be able to do some algebra here to obtain g of x here. And of course, we're going to have the typical issues that sometimes indexes are not starting at the right place, and that this type of thing here, they're not, like these are matched, but these ones are not matched. So let's start by making the indexes in the right place. So on the left here, this starts at 1. We would like to start at 0. So just write it out as what we want. So at 0. But if you subtract the first term, these two now are the same, right? Once again, this this here is this term without the a0, which is the same as just starting at 1. Okay. Now, for this one here, we want to match the powers here. So the way we do that is we can factor out an x. So this will be 8x summation n larger or equal than 1, an minus 1, x to the n. And for this one here, this one is actually a geometric series. So summation of powers of something x to the n, we know that this is a geometric series. Let me write it down here. So recall that 1 over 1 minus rx was summation r to the n, x to the n larger or equal than 0. And so this is going to be the case with the 10, as long as we also get it. So we could replace a 10 here and get 1 minus 10 here, but we need these things to match. So we do the same thing. We're going to factor out an x, and so we will get summation here for n larger or equal than 1, 10 to the n minus 1, x to the n minus 1. And let's make this blue. Okay. So here, let's solve the issues that we have. So, here actually I said it, but I didn't write it. Since I factored out the x, this is like this. Okay, so now we have this part over here. Let's isolate it here. So now this part over here, it's essentially the n starting at 0, right? Because it's with the 1 here. So it starts at 0. So this actually is already equal to exactly this here. So this starts at 0. So this is correct. And this one also starts at 0. So it's correct, because you can just do the shifting thing. But if you just check, you'll see that they already start in the right way. Okay. So that means that the one on the left here is going to be g of x minus a0. We know that a0 is 1, so let's replace it already. G of x minus 1 equal to 8x g of x plus, so this is going to be this geometric series here with the r equal to 10. So this will be x over 1 minus 10x. And now you can solve for g of x. So throw this to the other side, factor out, throw everything and isolate. And you will get that g of x is equal to 1 minus 9x divided by 1 minus 8x, 1 minus 10x. And let's copy this for later. Okay, so we found our generating function for our sequence. And now we would like to see if we're able to find the closed form. And the technique here is, again, partial fraction decomposition. So if we have this over here, in this case, the bottom part is already, factored. So we don't need to solve anything in terms of factoring the polynomial. We don't need to find any roots of polynomials, I mean by that. And so if we do the partial fraction decomposition, the idea is that you can write this as 1 minus 8x plus b over 1 minus 10x. And then the idea is that you multiply both sides by this bottom part, and then you equate, you like match coefficients. So the coefficients of the constant part here with the constant here, and with the term x here, with the term of x here. I do recommend you do this slowly at home, or like do it slowly yourself. And what you should get for this case, you should get that a plus b is going to have to be equal to 1, and minus 10a minus 8b equal to minus 9. So you have to solve this. And solving this, you get a equal to half and b equal to half, which means that our g of x is going to be equal to half 1 over 1 minus 8x plus 1 over 1 minus 10x. Once again, we have the geometric series. The 1 over 1 minus rx is the summation n larger or equal than 0, r to the n, x to the n, which means that this is a geometric series for 8, and this is the geometric series for like powers of 10. And so this means that our g of x, using the geometric series formula, is going to be equal to half summation n larger or equal than 0, 8 to the n plus 10 to the n, x to the n, which means that we have the following closed form for our problem: 8 to the n plus 10 to the n divided by 2. So how many valid code words, so n-digit numbers with an even number of zeros are there? They're going to be 8 to the n plus 10 to the n divided by 2.